I think you realize that assignment 2.3 is study goals 14 through 18, which is the end of chapter 5. I always do this. Please notice it's due after we discuss the content that it covers. 14 through 18 are carbon cycle, nitrogen cycle, and others. And I'm asking you to do the homework after. This is, I think, the only time in the year. It's the only assignment I can remember where you do the homework after the fact. The stuff in your book is fine, but I kind of like to answer these in class straight up rather than have you look at the book first. Then you go look at the book and answer the parts that I don't answer. There are a couple things I don't answer about your homework. So today you're going to start from scratch, 14 and 15. Yes?
Do you suggest them doing the assignment after the lesson?
Yeah, I think when you look at the book, you'll realize from your notes, like, leave a little space to write, but I think you'll... And I do this a lot. I just drew all this freestyle. It doesn't really make a lot of sense to anyone, myself included. So what I recommend is, when I point at something, then you write it. If you just copy this, warning! If you just copy this, it's not going to help you much. I mean, does that help you now? Okay, then don't copy it. Otter case, eh? Dude, these things are such a POS. Like, they have a 12-month guarantee, and then on the 13th month, they like... Look at this.
I know.
And then I have one of those for my other phone, my first phone.
They used to be really, really good, because when I got my first iPhone, it like lasted for like 2 years. And then this one I've had for like 6 months.
I was late to the train, so everybody's like, oh, get the iPhone, okay, great, I'll get the iPhone, sure. And everybody's like, ooh, bro,
Yeah, they're terrible.
$40.
I know.
Alright. You are so glad you're here today. If anybody was absent, this would be a really bummer day to miss. I would recommend you use like multiple sheets of paper because there's going to be a million little details. All right, here we go. Number 14. Go ahead, sorry.
So we're supposed to be doing assignment 2.3 like right now instead of...
Yeah. Like this will be about a half of your assignment. 2.3. We'll do another like 30 or 40% of it on Monday. So your homework due on Tuesday is the 10% of the assignment that you need to book for. I have to assume that some parts of number 14 you've already heard. We will start with the real basics. There's this thing called photosynthesis, which is CO2 and water being made into glucose and oxygen by plants using energy. So this is the part where, like, now you would be writing it. CO2 and water using solar energy are the R for reactants or reagents. Only plants can do this. They produce glucose and oxygen in photosynthesis.
So oxygen is just a waste.
Wait.
Yeah.
For that reaction, yeah, absolutely. Yes, hi, hello.
What's the, like, it looks like a E.
That's energy.
Oh, energy.
Anytime that I draw the backward 3, that's energy. I do that all year, so thanks for asking. I'm going to use that all year. Lowercase e is electrons or electricity. So we've got our photosynthesis. And the second half of what I hope you learned in biology and probably in chemistry and probably in life science and probably in earth science. I mean, how many of you recognize the terms, at least, photosynthesis and cellular respiration from your science? Yeah, okay, that's my point. Like, you've seen this. Just to be clear, you must know the chemical symbology and the names alike anytime in this class. If I throw the chemical symbology on the board, you got to know what that is called and how it is written. And unfortunate, this is a college level class where science literacy includes that level of chemistry. I'm sorry about that. Glucose oxygen from carbon dioxide and water is photosynthesis. And this part's really easy. The opposite is called cellular respiration.
What are the things in the circles like R and T?
Reagents and products. So what reacts and what is produced. Here's why I said that. And before you write, look at me. These are produced in photosynthesis, and those are the reagents in cellular respiration. So the stuff that comes out of this one is the stuff that goes into that one.
Okay, so that half is photosynthesis.
That's right. This half is photosynthesis. The same stuff on this side, cellular
Okay,
respiration.
and one at the top is an R.
Yep.
Okay.
RP, RP. Thanks for asking that question. I think I probably helped other kids. Right?
Yeah.
Want to start notes down? I'm going to come back to all these other words on here. I'll describe every single tick mark of the pen. But what I said so far, what is photosynthesis and what is cellular respiration? Just the ingredients so far. Are there any questions? Yeah.
So the energy on the very left,
Uh-huh.
what is that like? Explain
We'll get to that later. I'll throw it on the sidebar. So I haven't talked about that yet. Thanks for asking. We will get to that. Here it comes. We'll do it right now. Why do plants make sugar?
Feed themselves?
How do they feed themselves?
Photosynthesis?
Really? Making sugar feeds themselves? If you're going to make a sandwich, is that when you fed yourself? Yes?
They eat the glucose that they make from photosynthesis.
Yes, they also eat the sandwich. See, here comes the news flash. What you've been taught so far, I'm guessing, doesn't include a very critical ingredient. I learned in teaching this. Like the whole class and I had an aha moment. Not like aha, but like, ah, moment. At night, watch me, plants do this. Plants make sugar to store energy. See, energy coming in storage. And then at night, they release the energy from those bonds. So plants do both of those. We can only do 1/2 of that.
So what does the person have to do with this?
We'll come back to that. Yeah. Sugar is effectively energy storage for the plant. It's like, oh, there's all these ingredients out here. I want to build some sandwiches and put them aside so I can eat later when I get hungry. We, unfortunately, are not capable of doing that. There's a big difference between plants and us. If I go out in the sun, I'm just getting sunburned and sweaty, and eventually I will starve. I cannot make my own energy storage. I need to consume the energy storage of others. Correct? So here's the big difference. Plants are autotrophic. They make their own energy storage. That's what it means. Auto is make your own. Troph is energy. So own energy, make their own energy storage.
Is not the energy coming from like the mouth, the body? Is that correct? We meant like being.
This is the energy storage. This is the energy storage. Then we are heterotrophs. We got to take somebody else's energy storage, and that's how we get our energy. That's what this E is on the side. And that's why I showed the humans. To make this distinction, they get energy from the sun and store it. We get energy from our food supply and then release it in this process. Understand the arrow on the left? Understand why I showed the human?
Wait, so the energy starts constantly going back.
The energy comes in our food supply, and that's where we get it from. It's a byproduct of this glucose digestion. We break up the sugar to get our energy.
And then we like release it back into the cycle?
We use it. We spend it.
Because how does it like go?
It doesn't cycle. It goes from the sun to the plant, from the plant to us, and we use it to like sit around and yell at high school kids and kick our sisters and stuff. Okay? There's no energy return to the plant. That's why we need the sun. No sun, no plant, no human. Check this out. Carbon dioxide. CO1O2, okay? Carbon, oxygen, CO2. Can I do that?
Yeah.
Carbon is cool because if you put energy into the reaction, you can stick carbon together. That takes work. And later on, when you split those carbons, that energy comes out. Carbon bonds are storage. But that's something you should probably write somewhere because that's a really critical concept. So here's what plants do. Plants use carbon dioxide. They spit out the oxygen because they don't need it. They go, that's crap. I just want to stick carbons together. If I had the right manipulatives, this would be a hexagon. But I'm a cheapskate and I haven't bought the plastic one. Okay? So 1, 2, 3, 4, 5, 6 carbons. That's glucose. Okay? This is carbon bonds that the plant can use later. So at night, when the plant needs to grow or make more roots or come out of the ground and steal the change out of your cup holder, the plant will go, oh yeah, split out some carbon, release that energy that the plant needs, and that carbon has to have a buddy or he won't come free, so they make CO2 and breathe it out. This is why we need to breathe. What happens when someone suffocates you? Is that you're not breathing in any more oxygen, so eventually the oxygen in your blood gets used up, and then your body can't free up the energy to run your heart and to send signals through your body. You can't break the carbon without oxygen. This is why we have to breathe. It's not that we need oxygen for some sort of Jose oxygen thing. We don't breathe for us. It's called cellular respiration because our cells need energy, and the only way to get the energy out of this is to go, hey carbon, got you a buddy, thanks, energy release, right there. That's where the energy comes from breaking up the carbon bonds. Yes?
For 2 oxygens, you need like that blends up with the carbon.
Huh?
Okay.
So we breathe, to answer your question, O2, right? And we breathe out CO2. Right? Okay. Yes?
And the 6 carbons are from energy, right?
Yeah, so they're basically 6 units of energy. There are 6 carbon bonds, and so you get 6 bits of goodness out of that. Just like my oxygen needed for breathing and making CO2 to go out, and carbon is stored in sugars, which are a bunch of energy, because there's a bunch of carbon bonds.
Mm-hmm.
Yes, Colton?
So plants take the CO2, where do they get the other carbon?
Who's on what now?
Plants take in CO2,
Uh-huh.
where do they get the other carbon atom?
They breathe in 6, that's not a balanced equation. So they breathe in 6 of these for every one of those. Does that answer your question?
Yes.
Fun fact, autotrophs, because they make their own energy storage, that's a word you got to know, it's vocab. We, on the other hand, are heterotrophs. Because we need to take that from someone else. That's got to come from another place. We cannot make our own from sunlight. When you take carbon out of a living, out of a non-living system, like the atmosphere, where it's just like, carbon in the atmosphere, okay? That goes into the plant, and the plant makes it into a living thing, like an organic molecule, something useful for life. That's called carbon fixation, which is a type of uptake. You're fixing it, meaning you're putting it into a form where it can be useful to life. That's fixation. Putting it into a form where it's useful for life. Fixation?
It's called carbon fixation.
Yeah, carbon fixation.
So it's putting carbon into a molecule.
Yes. Also, it's putting carbon into a form where it's useful for life. It's called fixation. And that's a type of uptake because you're taking it out of the environment. Now, basic ecology 101, and then we're going to move on to number 15. Basic ecology 101. Imagine my food web, okay? Plants get their energy from the sun. Then crickets get their energy from the plants. Frogs get their energy from the crickets. Seagulls get their energy from the frogs. house cats get their energy from the seagulls. Jose eats house cats. House cats. And the shark eats Jose to get the energy from Jose. And the shark is torn apart by a pod of killer whales and sinks to the bottom of the ocean where the worms get their energy from the shark. Do you realize that all life on Earth is based on that first step, which was the productivity of the plant? Sunlight? All life on Earth is either making sunlight into something useful or eating that and 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 eating that. You know what I'm saying by that? Does that make sense to everybody? Yes?
Unless, of course, you're a chemo autotroph.
Delivered. Which is about 0.005% of the life on Earth does not. They don't use sunlight. This is actually called photoautotrophy. It's an autotroph based on light. Photoautotroph. Y'all know what I'm saying by that? Make sense? But now we get to that other thing, that little tiny bit. Thank you. Checks in the mail. There's a little tiny bit of life on Earth that doesn't rely on sunlight. Way down in the depths of the cold, dark oceans. You ever heard of those like black smoker things, those chimneys that spit out really hot water? Because like a little bit of water makes it through the Earth's crust, and they get superheated by like red hot magma, and like it comes out super hot, and makes like clouds, and as it cools off. Yeah. I hate it that a lot of you don't know this chemistry, but there's a really simple thing you got to know. Some chemicals hold together at high temperature, but fall apart as they cool off. So, way down deep, that water gets really hot because it's up against the red hot magma. And that water gets super hot, like 400, 500, 600 degrees. It would boil if it wasn't under so much pressure. And at that temperature, you get these compounds that are stable at 400 or 500 degrees. But when they bubble out into the bottom of the ocean where it's like 300 degrees, sorry, negative 300 degrees, that's super cold. That's actually not that cold. Negative 100 something. Whatever. Really cold? Whatever. It's cold. Bottom of the ocean where it's really cold, those chemicals will destabilize and go boop. And when they spontaneously break down, they give off energy. And there's bacteria that just live there and harness that energy to make their energy storage. And so that's a very small percentage of life on Earth that makes their own energy storage compounds from the spontaneous decomposition of large chemicals. That bacteria doesn't work anyplace else because you can't find that chemical energy anyplace else. It only works right there, like right at the top of those chimneys. Like right at the lip where the water comes out super heated and those chemicals go, yeah, oh no, too cold. Bloop. At that split second, there's bacteria and like gobbling up those chemicals. And inside those bacteria, when they cool off, the bacteria is like, yes, energy. And it goes, bloop, and it builds its own, I don't think it's glucose. I think it's something else. Yeah?
Aren't there these little like crab things that live down there and feed off that bacteria?
And so there's a whole food web.
There's
There's
like
like filter feeding worms, and crabs that eat the worms, the little jellyfishes.
It's like, you should just look at the picture of a hatchet fish.
You shouldn't even know.
And show it.
Because hatchet fish are rad and deep sea stuff is rad, but hatchet fish are capable, they dabble in all the food webs down there. There's a point where these things like rub against each other Because like sharks that eat crabs, they'll eat those crabs from the vents and they'll eat a crab from somewhere else. It's not a completely isolated food web in a bubble, but it is a small percentage of the planet's life that's based on chemical energy sources as opposed to sunlight energy sources. And this is like a fascinating field of study because apparently the chemical pathway that does this is much, much simpler than the chemical pathway that does this. And so people argue that the first life on Earth was probably chemoautotrophic and photosynthesis was like a fluke after the fact. There's other people who argue this came from like meteors and life on Jupiter or something. Because it's such a novel, such a separate chemical pathway, it's so unique, that there's like two types of life on Earth. There's the stuff that you and I are a part of, and then there's like that thing at the bottom of the ocean. Which also happens in puddles along the edges of lava flows, and also happens in like high temperature geysers. They're called extremophile, like they love extremes, extremophilic bacteria. All right. Did we do all this? Is there anything else to talk about then? I'm all yours. This is the time. Yes? Oh, so that's the part where it goes from a living form into an atmospheric, non-useful life form. So watch me. I will do a biological release for you if I can find more markers. You ready? Biological release. Look, this is the cheapest. This is the cheapest model in the history of science. If that doesn't work, please tell me. Say what? Yeah, right. Release. Release of bad breath. All right. Everybody look at number 14 if you had your study guide. It says... You want to ask me or are you good?
So you said it goes from a living form to atmosphere?
Yeah, right. It's something that's outside the biosphere.
Okay.
When you go from living stuff, from biosphere to another one, that's release.
Okay.
So it's left the biosphere and entered the atmosphere. See, I am biosphere because I'm alive. That's atmosphere because it's not alive. Okay, watch. Number 14 says, first describe the biotic carbon cycle, the parts associated with biological processes. Got it. What are reactants and products of photosynthesis? Reactants, products. What are the reactants and products of cellular respiration? Got it. Reactants, products. You should be able to follow a single carbon atom from the atmosphere into a plant, through photosynthesis, into an animal, back to the atmosphere, cellular respiration. Anybody want to ask me anything about number 14? I gotta remind you, there is no like balance. This is not like harmony in nature. The plants don't make oxygen for you. They don't know you're here. They don't like you. They're putting money in the bank and we're robbing their bank. They're the only ones that have figured out how to store energy, and so all the rest of life on Earth that's not an autotroph, all of us heterotrophs, we're just stealing from each other until the energy runs out. Somebody asked, where does the energy go? The energy doesn't go anywhere. The energy comes into the system and is eventually spent. You realize that, right? Like once I've eaten my breakfast burrito, I'll work it off, and then like, oh, I got more energy.
If there's already going to be all the mass, there's already going to be all the mass there is, can't energy not be like kind of destroyed or?
Well, it just changes form to a point where it's useless. So you can't do anything with like latent body heat. That energy is measured. The amount of calories I eat or the amount of calories I put off as heat, calor. So like when I eat 1,000 calories, I will like give off 1,000 heat units. It's just that the 1,000 calories coming in are high quality energy, so they can run me. That heat coming off me is not useful for much of anything. So the energy is neither made nor lost, but it does change form from a useful form to a less useful form. You said Newton's first, I said Newton's second. All right. I want everybody to remember that the biotic carbon cycle has carbon holding energy and carbon not holding energy, but that carbon's always moving around. Energy is a one-way street, carbon's always cycling. Agreed? Now, keep in mind that most carbon, whether it's being eaten and breathed or decomposing, that carbon is being cycled. That says decomposition right there, which is recycling of carbon. Everybody check out my log. This is a log. Okay? It's a stick that came off a tree, you know. And that stick that came off a tree, if I put it in my wood-burning stove, will give off heat to heat my house, and will also give off CO2, right? What happens if I leave that stick on the ground and let it decompose so that the termites eat it and then the mushrooms eat it? Will that give off CO2? Yeah, the exact same amount. It'll give it out more slowly. By the way, it'll also give off the same amount of heat. Those mushrooms and those termites will get it. They'll reuse that energy for something else. Carbon is either stuck together using energy or breaks apart releasing energy, but the same amount of carbon is always in the game. Clear? And the biotic carbon is either breathing, digesting, or if this animal like dies on the side, okay, then the worms are going to digest it, and then they're going to breathe out the CO2. Clear? But sometimes, little tiny bits here and there, like a human that got stabbed with a sword, or a poop. Thank you. Or an ant. I've raised 2 babies. I've seen poop like you wouldn't believe. Or a maple leaf. Or like fingernail clippings. Sometimes there's a little bit of carbon leakage out of the biosphere and deposited in sediment. I'm using all kinds of vocab words as I go. I mean, you see what I mean about like the vocab is just embedded in the content, right? This is a really hard lecture to give. Like, you have no idea how like heady this is for me. You can call this leakage, like carbon leaving the biosphere, because, you know, like that poop will get carried by the stream, and instead of decomposing and the beetles getting it back into the biosphere, sometimes that poop just gets buried under sand and that's lost in the ocean.
Then upwelling will eventually bring out that nutrient.
Maybe. But sometimes, that simple organic material, watch me, slowly will squeeze slowly into fossil fuel. Because look, it's called lithification. You take time, pressure, and heat. And that sediment starts to sandwich, sediment plus carbon plus sediment squeezes into the fossil fuel. That's a slow process. Like 150 million years at least, 250 million, 300 million years. Pretty slow. Time, pressure, and heat. T plus P plus H. Yeah, bro.
So as we use all our fossil fuels, like from 2 to 3 million or 300 million years ago, or however long it takes to make this, is new fossil fuels like popping up? Or is
Yes, it is. At a rate of that volume per 2 to 300 million years. Yeah.
we just use more than it?
That is so bingo, dude. You just blew my whole punchline. I got like 20 minutes of talking left, and now everybody knows where I'm going. But yeah, that's exactly spot on. Right. Correct. Yes.
Nice job.
Come on, James.
Don't say that again. Stealing my thunder. You will fail, young man. How dare you. Look, we call those carbon sinks. Places where carbon leaks out of the biosphere and enters the lithosphere. Those are called sinks.
Carbon.
It's all on there. You know what I'm saying. Carbon leaks out of the living stuff and gets into the rock stuff, yeah?
What does it say? Like, the carbon, there's a little circle.
Decomposition.
And then the one,
Leakage.
okay.
So if there's only a certain amount of carbon on the planet, wouldn't we run out of carbon because it's all turning into rocks? No, because rocks don't last forever. It's called weathering. So like that sediment will be eroded by rainfall or will go up into the air because of volcanic eruptions. There's other ways. Lightning strike, fires. Carbon dissolves into water and gets made into compounds that are useful to life. I must interrupt you for a key concept. Message from our sponsors. Watch. There's only so much carbon on the planet. Some of it is like juggling around in the biosphere, okay? Some of it is like floating around in the atmosphere. The atmosphere is really small, it's really thin. Layers around wrap on a basketball. There's not a lot of atmosphere. There's a little carbon up there, little carbon around here, like we're all made out of carbon. Plants are all carbon. That plant dies, now the worm's got the carbon, now the worm farts, now the air's got the carbon. Now another plant breathes, now the plant's got the carbon. Okay? Everybody go with me so far? Fixed amount of carbon in different places. Like there's a certain amount of money in the economy. She has more than me, she has less than me, whatever. But there's only a certain amount going around. Some of us spend it, some of us save it, right? Some of us spend it, some of us save it, right? There's a fixed amount going around. Nobody says it has to be even. It's just like different places, different times. Sometimes she's got all the money, sometimes I spend it, sometimes she saves it, whatever. Good so far? Now, if we're going to use the money analogy, sometimes some crazy gold miner buries a few coins in the ground and then dies in a bar fight, and that stuff's left underground. Did you guys hear about that family that found like a huge can of buried gold treasure up in the Sierra? It's like $10 million of gold.
Yeah.
Yeah.
We have like a little, like my uncle lives up by there, and Yeah, we have like a little house that we rent out up there, and it's like right around it, near Dutch Flat.
Can I go hunting there? Okay, fine. But that was near your house.
Well, kind of like they knew the people that found it, but they knew of them.
Wow, far out. You see, that money that leaked out of the economy, long time later will eventually bumble out of the rock. See? You like my analogy here? So, like, some amount of carbon is just living in the rocks, and then sooner or later it'll come out. Somebody said in the last period, well, if there's always the same amount of carbon, why is there global warming? Here it comes. Because humans figured something out. Humans figured out that if you punch a hole into the rocks, you can throw your cowboy hat in the air and yell "Yeehaw!" and you can be president. And you can take that stuff and you can put it in barrels and you can deliver those to the gas station and you can fuel up. Your SUV. And you can go, and you can drive away, run over babies. And as you're running over the babies, here's what happens. Your car is getting the energy out of those carbon bonds. Just like you eat sugar and inside your stomach you go chop, chop, chop. And then you release CO2, making your energy. Well, you know what fossil fuel is? It's a whole bunch of these stuck together in a lot of carbon bonds. And inside your car, when you light that on fire, your car goes chop, 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 and gets all this energy out at once, like thousands and thousands and thousands of calories per second, and goes, makes this giant CO2 explosion.
So it gives off more carbon than the actual
Say what? So proud of me. That was good, right?
That was it.
Thanks. Yeah, here's global warming in a really easy wrap. The atmosphere doesn't hold that much carbon. Most of it is either in life or in rock. We are speeding up the rock going back to the atmosphere. You know how we could fix global warming completely? Make rock really fast. But we can't. Yeah.
Wait, what's the red arrow?
That's all the extra carbon. That's the fossil fuel carbon.
What is it coming out of? What is that trying to
That's
It's an
oil.
oil well.
Oh.
God! I hate your drawings too. I think it's easy, man.
What's the little curlicues?
That's like the carbon underground magic. That's the part where carbon compounds from life have to be squeezed together into fossil fuels. You see, they're called fossil fuels because they're made out of stuff that used to be biotic. They're not made out of fossils, by the way. Please erase that. If your warm-up says they're made out of fossils, cross that off. Not true. Fossils are rocks that are shaped like things that were alive. Nothing to do with carbon. A fossil is like a sculpture that looks like something that was alive. Do you guys know how to make bronze sculptures using wax replacement? Maybe you've heard of this, wax replacement? Okay, watch. I'll teach you how to make a sculpture, and then we'll make a fossil. Watch me. You carve a pretty thing out of wax, like candle wax, beeswax. You pile up sand around it and pack that sand. Pack it all up. Then you take molten brass and you pour it. Bronze. Take molten bronze and you pour it into that mold, and as that hot stuff touches the wax evaporates and the bronze replaces it. Then you shake off the sand and you have a bronze statue. How many of you have heard of this? Okay, wax replacement, bronze statuary. You make a positive, build a negative, replace one positive with the other. That's how fossils work. You take a dinosaur, bury it in sand, pour some water through it, and as the dinosaur rots, the water makes crystal stuff in the shape of the dinosaur. That's a fossil. It's a rock that looks like the living thing.
And so it's not actually part of any of the original?
Usually not. In some rare cases, you do preserve some of the material. So like when wood fossilizes, if I'm not mistaken, the lignin remains. Which is a carbon compound, by the way. But most fossils are rocks that are shaped like the living stuff they've replaced. Fossil fuel is this. Random organic material that's been compressed with time and more time and more time between rocks. So you basically squeeze all that carbon into these long carbon chains. That's fossil fuel. Like tar is like 200 carbons together. Gasoline is like 15 to 17.
Would it be more efficient to burn tar in our cars then?
Oh, well, you're going to get the same energy because there's the same, like, the energy is proportional to the carbon bonds. Look, here's the funny thing. If you could get the engine mechanics right, you could burn paper, plastic bags, gasoline, tar, or babies. And the same amount of carbon would be used for the same amount of energy to make the same amount of CO2. Those are always going to be the same. Carbon bonds equals carbon bond energy equals carbon dioxide leaving the reaction. Yeah?
I think what he was trying to say was, since tar has more bonds, could you use less tar for more energy than if you use gasoline?
A volume of tar, like, there's another detail here about impurities, but let's ignore that. A gallon of tar is the same carbon bonds as a gallon of CO2 compressed to the same carbon density. Like, the energy is proportional to the carbon. So whether it's in one 200 bond chain or 20 10 bond chains, it'll occupy the same volume roughly, and you'll have the same CO2 roughly. There are some adjustments there, but they're pretty subtle. Yeah?
What's the missing carbon sink?
So, when we map the globe, now that we've got like satellites and like X-rays, voodoo magic, leprechauns, we can look at the globe and be like, there's so much plant equals that much CO2. And there's so much carbon in the atmosphere. And on all the earth, there's so much carbon and fossil fuel. And if you add up all the carbon we can find on the planet, there's a little bit missing. Meaning, there are like really accurate numbers for all of these carbon reservoirs. How much is plant, how much is animal, how much is in the air, how much is in the rock, how much is dissolved into water, how much is bonded into other chemical compounds. And until recently, there was like a teeny little bit of carbon that nobody knew where it was going. Like the equation wasn't quite balancing out. It's like, we got a crook around here, there's a little money, we can't explain where it's gone. Coincidentally, that's been solved now. Or most of it has been solved now. We've reduced the carbon sink by about 90%. Because we figured out that fish make carbon compounds in their gut and then they poop them out as sand. You want to know the missing carbon sink? Girls, you all need to know about this. Anybody know which chemical you use to build your bones?
Calcium?
Calcium. Anybody know what osteoporosis is?
You don't have enough calcium?
You don't have enough calcium. You don't have enough calcium. It strikes women more than men because, unlike men, women sometimes make babies. And that baby, to make its skeleton, sucks the calcium out of your body. You guys realize this? So when you get to be an old woman and you've made your 20 babies, well, a lot of your calcium supply just went into all their little bones. So women are extra susceptible to calcium. And apparently, you guys know what makes the bubbles in soda and beer? It's a what kind of beverage? Carbonated. Carbon. Sand is calcium carbonate. That's what shells are. Like seashells, calcium carbonate. So girls, when you drink soda, that carbonate reacts with calcium in your diet and turns into calcium carbonate sand in your gut. So girls, when you drink soda, you're pooping out little bits of sand. That's calcium you probably should have kept so you don't get osteoporosis later in life. Carbonated beverages are partially responsible for osteoporosis. And if you quit carbonated beverages, that includes beer, you could drink it flat. Might as well just gouge your eyes out with red hot poker, but anyway, that's the missing carbon sink. Because there's carbonate in salt water, and so when fish eat calcium supply, especially fish that eat bones, the carbonate in the water bonds with the calcium in their gut, they poop out little bits of sand, and that's most of the missing carbon. Have we blown binds today? Did this make new knowledge for you? Can you ask me questions or something?
Is that it?
That's it. I'm done. Ready to take a nap. See you later. Bye-bye.